This is zebra testosterone is one of them, and the other one is just fish oil.
Why don't you just eat fish?
Huh?
Why don't you just eat fish?
Well, I don't know. Talk to my endocrinologist. He put me on all these things.
I can't even pronounce that word.
Fish oil is good for you.
Huh? Yeah, the shaman.
The shaman.
This is my shaman. You got me on 600. Huh? Yeah. Yeah, I mean, the pills only... I only had problems with the pills just that once. It was a little of a balancing issue. We're fine. Oh,
that was weak. That was with max volume.
so first, a couple announcements. First one is, if you notice on General Chat, tonight we're going to watch the Steve Jobs documentary in here at 7:15. Won't cost you a dime. I'm going to try to make an appearance, but no promises. But Tim will be here, and there are several other people who are coming, so I highly recommend it. It's not like the stupid Steve Jobs movie. It's actually like a legitimate documentary called The Man and the Machine that was done very well. I've seen it. So it's very computer science history type stuff. So if you are interested, this room at 7:15.
I have to work.
I don't really care. I wasn't really actually inviting you. I was inviting everybody else.
I'll watch it on my projector.
Yeah. So in any case, definitely worth coming and seeing. If you're anybody here interested in that, by the way.
Which one is it? Interested,
Anybody? Wait, don't you have class tomorrow?
Who wants to come back to school?
It's my 25th birthday, so.
Don't you have my class tomorrow?
Yeah, he's going to skip so he can get drunk.
Yeah, just so you know, I often will give quizzes on the Wednesday before Thanksgiving
And by often, he means every time.
as an attendance-taking exercise.
So if you're in 390, show up.
Yes. Speaking of which, anybody want to go fishing after class today?
If I didn't work.
Huh? Who said sure?
Sure, let's do it.
You want to go?
Why not?
Don't let him touch my fishing
Do you have a
poles.
coat?
I have a coat right here.
All right.
Yeah, don't let
I
him
mean, we're going to go like 35 miles an hour.
That's
And,
fine.
all right.
Don't let him touch
Hey, hold on. Don't you have senior seminar?
Yeah.
You can't skip class. I'm not letting you skip class to go fishing. Does anybody not have class that wants to go fishing?
Sure, I can say I don't have class.
That can go fishing?
Where are you going fishing?
Milwaukee River here in town.
I want to go.
I just got to run to my house, get my boat.
I want to go with you so I can out fish you again.
That only happens that once.
It's true.
All right. So the first announcement, the first legitimate announcement was the documentary. Next thing, you guys saw me yell at you on general chat. Keep in mind, there's other people who view Slack, like deans and other faculty members and things like that.
Probably somebody equal opportunity.
I get it that most of the time you guys are joking and a lot of you are friends and have, so nothing on there was meant to be horrible. But the punchline is that the general chat is for a mixed group. So if you want to create a private group for those types of conversations, feel free to do that. That's what it's there for. But just like you shouldn't come into class and drop loud F-bombs that we hear down the hall and out in the hall. And the dean has also heard. Oh, and it's not just you. There's other people in this room who've done it as well. At some point, you got to learn that there's a time and place for everything. And if that's coming from me, I'm the most inappropriate person I know. All right? Okay.
Why do you have your DP on?
But there still has to be a switch that you can turn off when you're in mixed crowd situations and things like that. So I would encourage you to practice that and maybe start doing that on Slack as well as in class. This is not something that's just in this classroom. It's also happening in other classrooms and not even just in this department.
That sounds too progressive.
So,
Those of you who don't know that man outside the classroom is very well contained inside the
so there's evidence that it's possible, is what I'm saying.
This is your job, though.
Christian worldview code.
Christian worldview.
I got you.
Nailed it. Yeah. Wait till you see your present. Would not be classroom appropriate.
This doesn't have anything to do with the thumbtacks.
Does it have anything to do
I
with
have no idea.
emails that we...
What was the question?
Does it have anything to do with emails you may or may not have received?
Oh, it has a lot to do with this.
What happened?
You're not gonna give him a hooker in church, are you?
I thought you said it doesn't have anything to do with thumbtacks.
Not the thumbtacks.
Emails.
They had a holiday special.
I'm not even sure what this is.
See, the best part of an inside joke is when it's still funny and you don't have any idea what it's about. Those are the best ones. Oh, yeah. Yeah, we're good. We got all of this. You guys can bring it back on my hearing. Okay, so let's see. That's that. All right, so we covered the documentary. We covered Be Adults. We covered Stop Cussing. What else do we have to cover? Oh, we covered Anybody Want to Go Fishing. We got No Takers. Yeah, well, you're not allowed to skip class. I would never let you skip class to go fishing unless it was like a really nice day. Huh?
Today's a really nice.
It actually is pretty nice, other than the temperature
It's not that cold.
No, it's
like
actually really nice for what it's been.
It's 43
Yes.
degrees.
and no wind.
That's warmer than last
Yeah,
time.
so I'll fish by myself, listen to my audiobooks. I'll probably have a better time then than listening to your crappy conversation.
And you still won't catch anything. That just means you won't see any fish.
Probably true, but at least I'll get an hour and a half or 2 hours of my book in. So it's win-win for everybody. Okay, so let's see. We had a homework assignment on recursion. How did that go?
30 seconds.
30 seconds. Okay, so let's talk about this. Before we talk about some possible solutions to this, let's talk about what recursion is. So the generalistic term, what the 10,000 foot view of recursion is when a function calls itself. Okay, in our world, it's when a lambda references itself from within itself by name. Right? That would be our definition in here. So when a lambda references itself from within itself by name. And what does that imply?
He's talking to the third person.
This implies that our lambda is stored inside of our variable environment with a variable name. We have a name-value pair where a legal value is a lambda expression. We already support that, correct? All right. Now, for the homework assignment, though, we were taking this one step further. It was to basically implement letrec, correct? Where we could have a recursive call within our environment. So within our let environment, rather. Okay. But the idea is it should be identical either way. Shouldn't matter whether we're calling it within a let or whether we're calling it outside of a let. A recursive call is a recursive call, and it's going to look up the function with the given name in the current environment, that in the current context that it has access to. Okay? So that's what recursion is. Now let's think about factorial. So the example we had was factorial, and I talked to a couple of you. It sounds like you were able to get factorial to work recursively without too much trouble, but perhaps it might not work for all recursion, is the concern. So we'll look at that. But if we look at factorial, let's take the factorial of 4. That's our function. Factorial of 4 is equal to 4 times the factorial of 3, which is equal to 3 times the factorial of 2, which is equal to 2 times the factorial of 1, which is equal to 1. Okay? So we actually made 4 separate calls to factorial in this particular case. We made our original call, and then we kept calling that guy over and over and over again until we finally tried to solve the factorial of 1, which we could just answer with literal 1. The factorial of 1 is 1. Make sense? All right. So we started off by multiplying 4 times a promise. So we have to wait for the answer of this guy. All right, so we need to call this guy again. How do we call that guy again? What does it mean to wait for an answer? We can't get the answer here, right? So if we're going to rewrite this in our language, what are we saying? We're saying times for, and then we're saying eval expression. What was it? It would be an app expression, right? Factorial applied to 3. Something along those lines. Pretty close to what we'll have in our language. All right, so we're going to call the eval expression on the factorial of 3. When does this finish? We're able to finish this function call right here when this guy actually completes, right? Okay, when does that guy complete? Okay, so this guy is reliant on this guy here, which is actually saying 2 times, actually what is it, 3 times, oh here, we're rewriting this, 3 times the factorial of 2, and then this is 2 times the factorial of 1, and then this is just 1. So we're able to unravel this. Okay? Now, was there anything keeping us from doing this in our current implementation?
Yep.
What's that?
That you're always going to evaluate before you check the conditional.
Okay.
So you're always going to be evaluating the next one without ever. So you're gonna evaluate. When you evaluate the factorial, you're gonna say, okay, I'm gonna evaluate the left or the true and the false.
Okay, so we have a dumb if.
Yeah.
Okay. So we have a dumb if implementation that tries to do both the true and the false expression, evaluates them both, and then only chooses the path that based on what the answer was. Okay. Well, really, we should only evaluate the correct path. All right. So we can fix that. Easy enough fix, right? Okay. What else? So let's say that's fixed. That was the break inside the if. If this guy is 1, just return 1. Else do this. We were boiling down to 1 and doing the other thing at the same time. Anything else in our current language that was limiting us to this? From doing this? Well, we supported recursion. Well, we didn't specifically support recursion in our environment. We supported the ability to store functions in our environment. We never actually implemented recursion. But this works as is without having to do anything else special, right? Why is that? What's the hint I gave you on Slack? If we mount one of those t-shirt cannons on top of a car, can that t-shirt cannon be driven around? Even if we didn't implement an engine and all this other stuff into it, we didn't teach a t-shirt cannon how to drive. It was built on top of a car, right? This language is built on top of a language that supports recursion.
We do have the computer science shirts as a marketing campaign.
You can use my card.
Yeah, sure. If you get a t-shirt cannon first, or build a t-shirt cannon.
You can build
Just drive around that line shooting them.
All right, so when we did this, we leveraged recursion built into Scheme, right? When we called eval expression on the factorial of 3, isn't that leveraging recursion? We were inside of eval expression and we called eval expression again. We leveraged recursion from Scheme, right? How is recursion actually implemented?
Like bare bones level?
Yeah, bare bones level. How did the makers of Scheme implement recursion? So if I go here,
Are they just using go-tos?
function to know about including a function in its own environment kind of thing?
Let's see, define fact to be a lambda that takes in an x that says if equal x1, 1, else times x fact minus x1. So that is a plain Jane scheme procedure for factorial, right? How does that work under the hood? So this is at the scheme level. So what does this say if we ask for the factorial of 4? This is actually going to boil down to 4 times the factorial of 3, okay? Which is actually going to boil, actually, hold on, it's factorial of 4. Let's write it in scheme. Fact 4 is 4 times fact 3, which is 3 times fact 2, which is 2 times fact 1, which is 1. That'll work in scheme, right? And that works in our language after we fix the if as is. How is it implemented at the scheme level? When I say factorial of 3 right here, I cannot finish evaluating this procedure until this guy finishes. And this guy doesn't finish until this guy can finish. And this guy can't finish until this guy can finish. And that guy can't finish until this guy can finish. And that guy can't finish until this guy can finish. And that guy can't finish until we finally get to here. And then we start unrolling the recursion. How is this actually implemented? Using all of your computer science knowledge up to this point, how do you suspect recursion is implemented under the hood?
But like a queue style data structure that puts it all onto a stack and then looks at the end of the stack where it has the one value and then pops and just keeps going from there.
So this guy is going to have some sort of data representation for a procedure call, right? Okay. Not just the procedure body, but the call itself. So maybe this version of factorial, the name of the procedure is fact, and then maybe the value of x is 4, for example, in that particular case, since we only have one thing. So maybe this is a representation, a data representation of that call. Make sense? This is a data representation of that call. That call. Of that call. All right, so each of these are data representations of multiple calls to factorial. Okay, and he mentioned maybe we put these guys on a stack. All right, so I'm gonna come to the next screen here. Let's just do this one. Actually, let me delete this. We'll label it. Paste one of these guys on here. So our original call was this guy. But that guy could not finish because we had to make a second call. So we pushed him onto the stack and made another call. This guy. He couldn't finish, so we pushed him onto the stack and made another call. He couldn't finish, so we pushed him onto the stack and made another call. and he could finish. So we popped that off the stack, evaluated it, got down to a 1. Pop that off the stack, evaluated it, replaced this guy with a 2. Pop that off the stack, evaluated it, replace this guy with a 6. Pop that off the stack, evaluated it, replace that guy with a 24. Pop that guy off the stack. That's our final answer. Okay, so recursion is implemented using a stack data structure. All right, but we need to remember the current state of a procedure at the time the recursive call was made. So again, making our connections to other areas of computer science, when we need to pause something for now and come back to it later. Where have we seen that recently in one of your other classes? Go ahead. Yep, so context switching, right? When a PCB has some CPU time, but now for whatever reason he's not allowed to have CPU time anymore. For whatever reason, these guys, for whatever reason, this guy doesn't get to be evaluated anymore because we have to wait for another answer. So we're going to put him on hold. And what's our context switch? Our context switch is to throw him into some sort of data structure for holding the current state of a procedure. Okay, that's going to be the name of the procedure and then probably a collection of all the variables and their current values in the procedure. All right, and then if we go down a little bit farther down the rabbit hole, if we want to think about this in a in a more, let's say, complete programming language, probably which line of code we were also on in the procedure. Let's take a function like merge sort. So merge sort has 2 recursive calls, right? So both of those guys are working at odds with each other. So we have to remember when we come back, not only what was the current state, but which line are we coming back to? Where do we need to pick up where we left off to finish executing this line of code? Okay, so we have a data representation language, just like JSON, just like XML, something like that. We can come up with our own made-up data representation language. It just so happens that Scheme is a language of lists. Therefore, coming up with a data representation language for this is fairly simple, right? All right, so given that, could we remember the current state of a procedure fairly easily? Well, we know the name of it, right? We had the variable name. That's what we went and looked it up. And we know all the parameters that we have. And we can get their values by just asking the environment what its current value is, right? But every single time we execute our procedure again, when we push 1 onto the stack and say, okay, you're on hold, we'll get back to you soon, and we go and execute this again, we have to execute it inside of a brand new environment, an extended environment, if you will. Just so happens that we already have an extend env for lambda, right? So we would get a more local copy of x. And the more local copy of x would do what? Well, it would have the new value of x. So the most global copy of x, the very first one, would have been x is equal to 4. That'll be in our environment. The next one, which would be a more local scope, would have x equal to 3. So this guy is said to shadow this version of x. The next local copy is x is equal to 2. The next local copy is x is equal to 1. So because we're always evaluating our procedures, our lambda functions, inside of a extended environment, do we actually need to keep track of the current value of x? Or are we actually already accomplishing that by keeping track of the environment in which this call to factorial should be evaluated? Every time we call factorial, aren't we extending, every time we call an app expression, aren't we, every time we call an app expression whose car is a lambda expression, aren't we extending our env for lambda, giving us a new, more local copy of x, with a new, more local value for x. Therefore, when we evaluate the body of that lambda, aren't we evaluating it in the environment that's going to have a more local copy of x than we had a minute ago? And as soon as we're done with that, we're back to the old environment because we only evaluated that lambda in the environment that we extended. And after that was done, we stopped extending. So if we think about our environment here, let's just keep our environment fairly simple. So the very first time we had an x4, then we extended that environment and gave ourselves an x3. Then we extended that environment and gave ourselves an x2. Then we extended that environment and gave ourselves an x1. And then we were able to complete that call to eval expression.
Wasn't the last one just 1, not x1?
No, because we did call it for a factorial of 1. Right here.
Oh, we did? Okay.
Yeah, you finally call factorial of 1, which then boils down to 1. So we never call factorial of 0. All right, so when we call factorial of 1, it will extend our ENV for lambda, giving us a new scope. So our scopes are actually lists of, so these guys are each inside of a list, right? This is what our environment actually will look like. It's a list of scopes. So here's our most local scope, which has in it a list of name value pairs, which in this case only has one name value pair, which is x is equal to 1. So we're going to evaluate our final call to factorial. So let's just do factorial of 1 here, factorial of 2, factorial of 3, factorial of 4. All right, so as we call factorial of 1 and we evaluate this, we're going to apply the lambda associated with factorial, which only exists one time, right? That's going to be way, way, way back here, probably in the very, an older version of our, so we have a fact, and this guy is a lambda exp. Let's just do ... there. All right, so that's our fact that we'll pull out of there. Okay, he's unevaluated at this time. So when we resolve fact, it's going to check the most local scope. It's going to say, is there a variable in here named fact? No. Is there a variable in here named fact? No. Is there a variable in here named fact? In here? No. Finally, we get this guy. So when we resolve fact in our environment, we'll pull out the lambda associated with fact, unless we had a more local copy, which is why our let rec, if you will, our lets already work as let recs, because they just create a local, they create a more local copy of a, in this case, a lambda in our environment. Okay? So every single time I extended the environment, I just put another scope on top. Another scope. Well, another scope on the front, another scope on the front, another scope on the front. So now I'm finally able to evaluate the factorial of 1 in this environment. All right? X comes in, or 1 comes in for X. What's the current value of X? It's this guy right here. So I'm going to get a 1 out of it. I won't bump into this X. I won't bump into this X, so on and so forth. A variable always resolves to its most local definition. 100% of the time, resolves to its most local definition. So I will get the 1 out of this. We'll calculate the factorial of 1. Factorial is going to be this lambda, so I'll call an app expression, passing 1 in for the x, and it's going to ultimately boil down to 1. So that call to eval expression has finished. And when that call to eval expression finishes, I bounce back to the world that has an environment that looks like that. I didn't purposely remove that first scope. I just went back to a world, a call of eval expression whose ENV variable looks like this, not like the last guy. Make sense? I removed the element from the front, but I didn't explicitly do it. It did it because of the way my logic works. So extend ENV for lambda, puts a brand new scope on front of my environment, pushes a brand new scope on top of my environment stack. Following this? We already had a stack built into our language, even though we didn't think about it. Okay. Remember way back when I said it was a good solution that Amish came up with for our environment being a list of scopes? Recursion would have been a lot harder to implement had we not done it this way. All right, so. So.
I still
What
hate
you're
you
saying
for
now.
it.
I planned it this way.
Yeah, land it this way.
What
Okay.
we're saying is that we love you, but we hate you at the same time.
So now, we just bounced back without us even, we didn't pop that most local scope off of our environment. It just fell off the environment because we went back to the previous call to eval expression. That is the call to eval expression that was called with this environment. All right? And that call to eval expression said to calculate fact for a value of 2. This is an app expression. So what are we going to do? We're going to apply our env, this env. So here we can always say that's the current value of env. We have multiple copies of env floating around depending on which call to eval expression we're in. All right, so we're going to go ahead and grab the value of fact, which is going to be this lambda expression. Okay, the nice thing that we would have with our, actually it'll look like this anyways, because potentially we could have an older environment, more stuff after this. So this is really looking at what our environment might look like within the let. Okay, so this is our let environment, extend env for let. That's going to give us this very first guy here where fact is equal to this lambda. All right, so now we're in this apply env. Okay, and this guy, our eval expression, so we're going to call apply env on fact to get the exact same lambda as we got before. We don't have multiple versions of fact in there. We have one of them. And then we're going to pass 2 in for that, which gave us this local environment. So we're evaluating that lambda from fact in the environment where x is currently equal to 2. We execute that. And we get 2 times 1. Bounce back to the previous call to eval expression. Now we're evaluating factorial in the environment where x is 3. Now we're evaluating a eval expression inside of the environment where x equals to 4. Finally, hopefully, we're out of calls to fact because we no longer have x's. We no longer have x's. All we have is our factorial there. And now our let finishes. So when our let finishes, we're no longer living inside of the call to eval expression that is related to that let. Therefore, we're now living inside of the call to eval expression that was originally called, which was called with the empty environment. So those things fall out of our environment naturally. That make sense? So, a couple minutes ago, we talked about a data representation language for keeping track of what a procedure looks like. We've bypassed that by having an environment of scopes where each scope now holds the most local copy of things. That's how environments work. Okay? If we change the way apply env worked, where apply env went back and found the first value, the oldest value of a variable rather than the most local. So this one statement, so a truth in programming languages is that all variables resolve to their most local definition. That's a truth of programming languages. Every single language you will ever work with, that's a truth. If you can't rely on that, all of a sudden the way we solve problems changes. Okay, so if we changed apply env to no longer return the most local definition, the most local value associated with the variable you passed in, but instead gave you the oldest variable of that, all of this logic now breaks. It's that one little decision about how apply env should work had a lasting, had a lasting impact on how the whole rest of the language came to be. Does that make sense? All right, so recursion is not difficult to implement as long as we can remember a state for a function call. We can either do that through environments of scopes, or we have to do that using a separate stack. We can do it with a separate stack that keeps track of, maybe in the scope or in our environment, our non-scope based environment, we have procedure IDs or something like that, which remembers the last call to a particular procedure. Maybe instead of factorial, maybe we have factorial :0, factorial :1 for various calls to it. And then we go and look that guy up. He almost acts like a pointer into the stack for which call to the to factorial is the one that we're actually dealing with, because we need to go and look up the value of x for that particular call to factorial so that we can make sure we do the right math. Make sense? Isn't ours better? Didn't we go into this assignment expecting it to be really difficult? Probably spending more time than we should have, only to find that it almost worked. Was laughed at lunch today when Amish said, "Oh, it just accidentally worked." When was the last time that happened on your 470 homework? Something just accidentally works. Okay? It works because decisions that we made leading up to this were compatible with recursion, and we were implementing this on top of a language that supported recursion in a big way. Scheme is. It wouldn't be a lie to say Scheme basically is recursion. All right. So having said that, let's think about an older language. Does anybody know of a programming language that does not support recursion?
Does Fortran use GoTo?
Fortran does use GoTos, but Fortran also does not support recursion. I think using GoTos doesn't necessarily.
Well, typically when you would see that, that's what I've assumed.
So so here's a language called Fortran, which is it's called formula. It stands for formula translation. It's a math-based programming language. This guy does not support
Who is Fortran?
recursion. I don't know. Fortran's probably 1970s or something.
I was just curious. I knew it was like old. I wasn't sure how.
Might be older than that. I think C is 68 or something like that. 1968. Fortran, I don't think was before C, because I think Fortran is a C-based language. They're
Google it.
66.
66? So then Fortran's not a C-based language. They must both be BASIC-based languages.
Oh, the draft was in 1955, and the first one appeared in 1956.
Of Fortran?
Yeah, it was 56, 57.
Look at you're on Wikipedia. That was the cruise ship we're going on.
Looks like fun. Is there a carousel on that?
There is.
You gotta write it?
We're going on the biggest ship in the world.
You gotta write on that, and you gotta take pictures.
Well,
What's
let
not-
me actually show this to you real quick, because we've been on the third biggest ship in the world.
Did you change ships?
Yeah, we did.
Oh, okay.
I canceled it, and one day later, we got a good deal on the biggest ship in the world.
I was about to say, because I know we were talking about this. The bumper cars and that?
Yeah.
You gotta ride the bumper car and take a picture.
I don't know. Will it allow him to ride the bumper cars?
He
They
should
better.
make it happen.
So yeah, so here's some interesting stuff. I think this is the
Does it have a driving range on it?
Waste of some.
this right here. That's the 5th biggest cruise ship in the world, next to the ship I'm going to be on.
How old is that ship?
2010 is the Oasis. 2011. Actually, no, maybe it was 2012 was the Oasis. 2013 was the Allure, which is the sister ship to this. Those are the 2 biggest ships in the world. And then the Norwegian Epic is the 3rd biggest ship in the world.
I'm going on the Allure.
The lure is the
Yeah,
large-
the Allure is the sister ship to the Oasis. I think one of them is like a foot longer than the other one or something like that.
The tonnage is the exact
Yeah,
same.
they're the same ship. Just one of them happened to be how they built it. It's some number of inches or something like that longer than the other one. They're both like 1,200 feet long or something. There's some ridiculous. But it's the third biggest ship in the world is the Norwegian Escape or Norwegian Epic rather. I think it's 165,000 tons. These guys are both 225,000 tons. They're like way bigger than the next class down. So yeah, that should be an interesting.
I really want to see a picture of you riding
The carousel?
the carousel and the bumper cars.
Well, there's also an ice skating rink. I'm going to go ice skating on there too.
That sounds dangerous.
Really?
You'll break.
Look, there's trees. Here's a park. Here's Central Park. You can go to park on this boat. Real trees.
Oh.
I clicked on the park.
This boat is not its own country because
They have a putt-putt course. And they have tennis courts and
as a coach shop.
Yeah, there's a coach shop. You can buy overpriced purses.
Oh, I'm sure there's super overpriced there.
Oh, sure.
Who wants to buy it?
Tax-free, though.
Wait, it's tax-free? Can you-
Yeah, because international water.
I don't think so.
Okay, it's tax-free. Can you bring me back cigarettes?
It's called the Harmony of the Seas.
Well, then you have to.
Oh, okay. That's their next ship.
Yeah.
Yeah, their Quantum series is coming out. Yeah, I didn't know the Harmony was going to be bigger.
Customs. You had to go through customs then on the way back.
Yeah.
All right, so let's go back to Fortran here.
Where are you going?
Huh?
You can pay taxes on it.
Oh, somewhere in the Bahamas. I don't know. We've been to all the islands. We go on a lot of cruises, so we don't even look where they're going. I mean, we care about the ships. Where my wife collects these magnets for every ship we've been on, so we got a zillion magnets for these different ships that we've been on.
So you're just those people that like.
Although interestingly enough, this one has 3 stops and 2 of them we've never been to. One of them is a Royal Caribbean private island or something, and then the other one is just a
They built
different.
their own island?
It's a Tortuga. It's a different island in a chain we've been to. So
So is it like, are you just those people that get on the boat and you're just talking to the people next to you and it's like, oh, where are we going? Like, we going somewhere?
no, we know. But we don't use that as the judge. We don't like oh well, we've already been to. I don't even know how many times we've been to Cozumel or something like that. Though, I mean, every boat stops in Cozumel. Every Caribbean trip. I mean, we've probably been to Cozumel 20 times. You just get off the boat. My wife shops for trinkets for 20 minutes. We get back on the boat and get the buffet. I mean,
It's like the best part. Always.
I know it is so good.
Are you gonna go on the rock climbing wall?
Of course.
I don't think they make a harness in your.
Actually, the reality is I hardly ever do any of those other things. I buy the rich people spa package. So they have all these big boats have the thermal suite on it, which is like this giant hot tub. Like the biggest pool on the ship is a hot tub that's like 5 feet deep and they're like full body jets and stuff. I just live in there. I get up, I go into the and you pay like $250 for the week. So you have to go up past so you don't have to bump shoulders with the steerage.
So you have a.
So it's just that and
It's a
golf.
spawning.
Yeah. I go in there. I just chill until I finally get a text from Tabby saying that she's finally gotten her butt out of bed and she's ready to go to breakfast. And I go meet her for breakfast, and I go back to the spot. Do that, and then meet for lunch. And then we meet for dinner, and then she usually drags me to some show. I think this one has cats on it or something, like the show Cats, and then it has another
I thought you
Cirque
meant,
du
like,
Soleil.
actual
No, this one has Cirque du Soleil, some aqua show. Like they have a theater on there that's made of water.
Yeah,
So this is
diving aqua theater show.
yeah. They have a high dive show
Ice
on a
skating
boat
shows,
on the water.
Casino Royale, bar hopping, design boutiques.
bar hopping. I'm down.
Yeah, so
Live
I
jazz
do the
club.
all you can drink thing, and yeah, I
Spas, food, and golf.
And beer.
And like,
I do wine. I'm a big wine guy, so I usually do about 3 to 4 bottles of wine a day, plus the spa, plus a lot of food. That's a good trip. Well, I mean, 4 bottles of wine a day is like half a bottle for you, and it's like 1 glass for large enough here.
drink wine.
Yeah, but if you did, it would be like 1 glass. I seem petite, but I'm like the size of a
You saying
bear.
He's a lightweight.
Let's go drink whiskey and
It's
then
not
we'll
like he's
talk.
gonna, drink all the wine and then just suddenly go up to like.
I'm sure I wouldn't like it, but I bet you I would be just fine for a while.
Did you go with the Russian? That's just like
All right.
I'm going to Indiana Sunday or Saturday. Maybe I'll bring back moonshine. You can try some of that.
Well, I'm not gonna like it. I can't stand normal alcohol.
Oh no,
I like wimpy drinks,
It
like
tastes
from
like
a flavor
apple pie.
perspective. Let's see here.
This
Okay, so a
little
bunch of different versions of Fortran. Let me shut up. Let me find a code example here. Here, let's just do a Fortran code example. And use Fortran examples. Here we go. Here's a recursive routine in Fortran from 77 and 90. Yeah, see, they actually tell you how to write recursive routines because they didn't exist prior to that. So here's our main program. We have two integers and an x. We have a subroutine, sub1. Here's some global variables. So x is equal to 0. Enter the number of repeats. So we read something into the variable n. Then we call sub1 with our x is 0. Well, the current value of x is 0. And then the subroutine is sub1. Let's see. Here's our subroutine, sub1. Takes in an x and a dumb sub, but dumb sub is actually sub1. Okay? So this is how it's pulling off recursion. Because it doesn't support it directly, we actually pass it in as a parameter, which means that in Fortran, functions were first class objects, just like they are in Scheme. So then we have our integer and x, we have our dumb sum, then here's our less than, greater than, blah, blah, blah. Call it dumb sum on x, dumb sum. Or dumb sum, whatever. All right, so they're showing us how recursion was ultimately implemented by just adding what? Lambdas to the variable environment. When we made this call to this subroutine, sub1, the environment was extended with two new values, or two new variable value pairs, name value pairs. X is equal to something, whatever was passed into sub1. In this case, it was 0 for the first time. And dumb sub was equal to sub1, which was equal to a lambda. Because this is that sub1, which effectively is a lambda, right? All right, so that's what Fortran looks like. So we actually look at this, and this is almost like a little intermediate language between assembly and modern high-level languages. Not a huge jump, but similar to it. Okay, so let's do this now. Oh. Gutter covers. Just randomly opened up some email. Luckily, Abe dodged the bullet there.
You don't know or you do know?
Do know.
That's right, you know.
Let's see. Okay, so let's get back into our okay, so just kind of taking us down the rabbit hole that the book takes you, but we've gone a different route. So here's a language with procedures. So we already have a language with procedures, but they have something in here called the proc expression, where a proc expression has a variable and a body. And so we turn our lambda expressions into this. But what we do is rather than pre-parse our lambdas, we store them, or rather than pre-evaluate our lambdas, we store them in a format that we can then apply them through an app expression later. So we, I guess, leverage our app expressions for multiple things. So here's an example of the language they have you build in the book. So let's just talk through this real quick, and then you tell me how our language would end up being different if we wrote it this way. So they're creating a let expression. Let f equal proc x, where it's minus x11. So that's the expression there. Right off the bat, notice this is not a list-based language. This is a string-based language. And we took the easy route in here by building a list-based language inside of a list-based language called Scheme. So by building a list-based language, we were able to use list refs and cars and cooters to walk through it, as opposed to having to take in strings like this and manipulate those strings into other things. So, for instance, what do we have right here? Let f equals this. So we're having procedure f. Well, this is them calling it inside of an app expression. But in our language, this guy would look like what? Let's just write that. So our language would have a let, and we'd have a variable environment. So here's our f is equal to, instead of a procedure, it's a lambda. That's going to be a lambda x minus 11. So this is actually a let expression. Lambda expression that takes in x minus x11. Closes that, that closes that, that closes that, that closes that. And then we get to the body of that guy, and that's going to be f of 77. So we have a couple of app expressions. So we have f of 77. That's the body. So this is an app expression, this is an app expression, so on and so forth. So our language looks like this. Their language looks like let f equal a procedure that takes in an x and minus x11, like that, right? X comma 11. And then they have an in clause. And this is going to be f of 77. Oh, that's actually interesting that their language down there is a list-based. By interesting, I mean stupid. F of 77. Seems to be not compatible with the first part of the language, but whatever. All right, so our language looks like this. Their language looks like this. What would be more difficult about going with their syntax? So our syntax, we write something that pretty much looks like Scheme, and have a scheme parser turn it into our data representation language for our language, right? Which is really just duplicating Scheme. We've kind of written Scheme inside of Scheme. But now their language would come in as a string like this. How would we turn a string that looks like this into our parsed objects? How would we turn that into a let expression? If this was our input, how would we turn it into this? Because I guess the reality is in our world, we don't actually say let expression. Ours looks like this. Let f be a lambda x minus x11. Yeah, because even this isn't even correct. In fact, I'm kind of wasting my time doing this. This is almost pseudocode, right? Because inside this is a lambda expression. This is a op expression. This is a var expression. This is a lit expression. This is an app expression. This is an app expression. This is a var expression. This is a var expression. This is a lit expression. So that line would be a whole lot longer is the punchline, right? If we were really to expand it out. So how would you turn something that starts off like this into something that ultimately parses into this? Rather than what we've done where we've taken something, you know what, let me just actually, this is an op. Ooh, you know what I'm going to do? I'm going to do this. No, I'm not. I was going to cheat, but I decided not to. That's an op expression. This is a var expression. This is a lit expression. This is an app expression. This is a var expression.
What's your op expression? Don't you need the?
Oh, yeah, I do. Thank you. What was it? Minus? Do we actually, did this guy have a, was he an op? Like, did we represent him as anything? Did we represent him as like an op minus? I don't think so. I think we just stored it. Var expression, and then this is an app expression. Hey. And then this is a var expression. And this is a lit expression. All right, so at the very least, just let's say that's close. All right, so this is the parsed version of our input. Our input language looks like this. Let f be a lambda x minus x11. And then the body would be f of 77. This is our input to our program. This is their input to their program. These are equivalents. This is Java. This is Amish. We'll assume this is Java. It's not quite Java, but yeah, this is our Amish language. Okay? Which actually seems appropriate, seeing as though the Amish language stays true to the underlying earth. The underlying language here. We haven't looked at newer, cooler things. We pretty much just do everything in terms of the constructs that were provided to us. All right, so these are two separate inputs that ultimately could get turned into the exact same parsed language. So the exact same parser can interpret either of these languages as long as we can convert the input symbols into this data representation language. Make sense? We just happen to choose a data representation language here. You know, we made one up, didn't we? For those of you who were at the hackathon in Raleigh last year, my team wrote an interpreter there, and we had a language whose data representation language was JSON, right? So same thing, right? The input comes in as something, and we turn it into something else. Our something else was a JSON representation. In this case, our something else is a list and symbols representation. This is more proprietary, but who cares? This makes a whole lot of sense if you're using Scheme. JSON doesn't make any sense, and Scheme has our cars and cooters and list refs that allow us to pull individual pieces out of this. Using Scheme, if I had given you an assignment that says take this and turn it into this, what challenges will we immediately have based on what you know right now? Steal this guy. So there's our input. It's a string, right? How does Scheme work with strings.
That can come up with some interesting things.
Oh, come on. Is the internet going to fail me now? I need to be able to give you this impossible assignment over break. All right, string to list. Let's look at what that guy does for us. Comment this out for a second. Just make sure this looks like the way I want it to look. All right, and let's do string to list of input. I think that's the right syntax. All right, so the car of that is L, E, T, then we get a space, so we can convert a string into a list, so that's pretty convenient.
And it can use lists.
Would we want to parse it to spaces then to get for another list?
Ah, that could be helpful. We can also turn a list back into a string. So, for example, if I do this, let me take the cdr, let's do C, DDR of this guy, so just something shorter, right? And then let's go back, let's do list to string of that. Starts getting individual pieces off of there. So I did two cooters. We got the two elements off the front. So we literally digest that guy. We can turn numbers into strings. We can turn strings into numbers. We can append to a string. Let's go back and show this piece here. What are you whining about now? What are you whining about now?
So I don't want to take more Vicodin.
Well, stop whining then. Just suck it up.
No. That's what Vicodin's for.
So take it and stop complaining.
You don't want to see me stoned in 490.
Oh, I don't care if you're stoned in 490. I'll be out fishing. All right, so we represent characters with a pound backslash T. Well, not the T, but the pound backslash represents an individual char. So the car of a string, well, the car of a list version of a string is kind of like taking the charat of a string, right? So if I have a string, and I want to write a method called charat, I can say define charat to be a lambda that takes in a string and an index. I could write this guy to turn my string into a list and then take the cdr of that index number of times and then finally spit out the car. That would give you the index of that, right? Okay, so you're swapping back and forth between lists and strings. All right, so backing off that real quick. Having said that, is this representation of our language worse than this representation of our language? Are they just different things of accomplishing the same thing? Isn't our actual language this? So this is evidence that programming is programming. It's not Java, it's not C#, it's not Fortran, it's not Scheme. At the end of the day, regardless of what the syntax we write the stuff in, it's going to be converted into something that either an interpreter or a compiler, or an interpreter or an assembler, knows how to deal with at the CPU level. This looks nothing like what we typed in. Couple little similarities there, but we really turned something that was relatively simple from a human eye perspective. In fact, this one, would you say this is simpler to a human than this one? The book's representation looks better to a person than our representation does?
Unless it's an Amish.
Because our representation is a list-based representation, and that's not something that human beings are necessarily accustomed to. We get caught up in all of these parentheses, right? We get the parenthesis diarrhea.
Yes.
All right? So we still get parenthesis diarrhea here, but this is more Java level parenthesis diarrhea. We only have parentheses when we're actually making a function call. Otherwise, everything's just kind of hanging out, right? Was that phrasing? Possibly. Right.
We'll count it.
Yeah, we'll count it. Christian worldview. All right, so in any case, are we better off allowing the human being to write simpler code and then having us as the programming language writer spend more time converting that into our data representation language, or are we better off making life harder for the programmer every single time they write the code?
Well, speed of issue.
Well, the goal of the programming.
You're just gonna run it through the interpreter once. So, speed might be an issue, but in a compiled language, it's a non-issue. You compile beforehand. So the answer to your question would then be no.
Well, then,
The real issue is computer languages are supposed to be power tools for human beings, allowing us to tell a computer what to do. That leverages our ability to write stuff. We've already seen this, that as we've written code, as we've written some of our procedures, we've had to sit there and screw around with where our closing parentheses are and stuff like that, making sure that what we're trying to that we're writing the thing that we're trying to test correctly. And that doesn't happen in Java, does it? Java, the code pretty much looks fine, or it doesn't look fine. In this case, we're counting closing parentheses and make sure we have it in the right place. All right, so we'll come back and we'll talk about, I'm either going to talk about turning strings into something else, or we actually might jump ahead a little bit in the book because I want to get to streams as well. Okay, have a good break, no homework.